Wow, you've really given us a fascinating, almost a daunting challenge this time, diving into, well, the very nature of reality itself. I mean, we're talking about smallest particles, the vastness of the universe, and then, all those mind-bending philosophical questions. It's a lot to unpack.
It really is. And it's striking how the sources you've all sent in, from, the nitty-gritty science to the much more personal reflections, it really highlights how complex this whole question of reality is.
Yeah, absolutely. So I guess our mission on this this deep dive is to try to weave together these different perspectives, the science, the philosophy, all of it, and see if we can arrive at a clear understanding of what reality might actually be. And we've got some really interesting material to work with, transcripts from channels like History of the Universe, delving into the physics and cosmology and philosophical essence, which brings in some very interesting experiential viewpoints.
Right. And for anyone listening who might feel intimidated, like, do you need a PhD to follow along? No, not at all. We're going to break down those complex ideas together step by step.
Exactly. So let's start with what seems like the most obvious starting point. For our early human ancestors, what they could directly sense, what they saw, heard, touched, that must have been their reality, right? I mean, their survival depended on it.
I think that's a safe bet. That rustle in the bushes, it meant food or danger. Reality was immediate and directly tied to their well-being. But then, as human thought developed, things started to shift. We began contemplating things beyond our immediate senses.
It's fascinating that some of the earliest evidence of burial rituals goes back almost 100,000 years. To me, that suggests that even back then, people were considering the possibility of an afterlife, a reality beyond this one.
Right, exactly. It hints at a growing awareness that maybe reality wasn't limited to what you could see and touch. There might be realms of spirits, gods, things beyond the physical world. And in those early explanations, something as simple as an apple, it would have been seen as a gift from the gods, a reality that was just accepted.
Yeah. No one was really asking why an apple existed. It just did.
Yeah.
But then came along thinkers who started to question those assumptions. Like Plato, for example, back in ancient Greece. He really grappled with the fundamental question of what's real, didn't he?
He did. And Plato's allegory of the cave, that's one of the most famous examples of this kind of questioning. He asked us to imagine prisoners who have been chained in a cave since birth. They can only see the wall in front of them. They've never seen the outside world.
Okay, I'm picturing it.
And all they ever see are shadows dancing on that wall, shadows cast by a fire, and people passing by the cave entrance carrying objects. For these prisoners, those shadows are their entire universe, their only reality.
It's a powerful image.
But Plato takes it a step further. He says, what if those shadows aren't even direct representations of reality? What if there are people behind a screen using firelight and puppets to create those shadows? To the prisoners, those puppet shows would become their world, their reality, even though it's all a carefully constructed illusion.
So what Plato's suggesting is that what we perceive as reality, what we think is real, might just be a limited perspective, a shadow of a truer reality that lies beyond our senses.
Exactly. And that idea is, well, it's surprisingly relevant even today when you consider how much of our understanding is filtered through our limited senses and experiences.
Absolutely. But our approach to understanding reality took a pretty dramatic turn with the scientific revolution, right? Instead of just philosophical reasoning, the focus shifted to understanding the universe through its fundamental component: matter, time, space, and using observation and experimentation as the tool.
That's right. And Isaac Newton was a key figure in this shift. His view of the universe was like a giant predictable machine, governed by precise physical laws. Time was absolute, ticking away at the same rate for everyone. Space was a fixed three-dimensional stage where all the action happened.
He saw reality as this direct manifestation of physical law in action.
Precisely. And even something as simple as white light, it held a revelation for Newton. His discovery that ordinary sunlight actually contains all the colors of the rainbow, and that raindrops act like tiny prisms to split that light into its spectrum, that was a huge breakthrough.
But here's where it gets interesting. Newton explained the physics of light, but the way we experience color, that's actually a subjective interpretation by our brains, right?
Right, exactly. It's not an inherent property of the light itself. Consider the mantis shrimp. This creature has 12 types of color-detecting cells in its eyes, compared to our measly 3. So their experience of color must be vastly richer and more complex than anything we can imagine.
12. Wow. That really makes you wonder what yellow even means, Like, is my yellow the same as your yellow? Or a mantis shrimp's yellow?
Precisely. So when we see a banana as yellow, that's just our human brain's interpretation of a particular wavelength of light. Another creature, with a different visual system might perceive that same banana as an entirely different color, or even something we don't have a name for.
Right, and sound is similar, right? It's our brain's interpretation of pressure waves in the air. So it really makes you question how much of what we call reality is actually a kind of virtual reality created by our brains.
It's a fascinating question. Now, if our senses are giving us this interpreted version of reality, what about space and time? Those seem like the most fundamental constants, the unchanging backdrop against which everything happens. Surely we can rely on them.
That's certainly what Newton thought. But in the early 20th century, Albert Einstein came along with his theory of relativity, and it completely revolutionized our understanding of space and time.
Right, the idea that time can actually pass at different rates depending on your motion and the strength of gravity. That's one of the most mind-bending concepts in physics.
And there's actual scientific evidence for this, right? Like that study from just last year, 2023, where astronomers observed quasars from 12 billion years ago.
Ah, yes. That study used the light flickering from those incredibly distant quasars as a kind of cosmic clock. And by comparing how those ancient clocks ticked to how our clocks tick today, they found that time actually ran slower in the early universe.
And that's because of the expansion of the universe itself, right? Space-time is stretching, and that affects how time flows.
Exactly. So time isn't this absolute unchanging thing we once thought it was. It's relative.
And it's not just the distant past, right? Time is also relative in the presence of strong gravitational fields, like those around black holes.
Absolutely. The immense gravity of a black hole warps space-time to such an extreme degree that time slows down dramatically for an observer near it.
It's like time is a river, and gravity can create rapids and whirlpools that change its flow.
It's a good analogy. And what's surprising is that this slowing of time near black holes, it actually has a similar mathematical description to the slowing of time in the early universe, even though the physical situations are completely different.
So time is relative, it's flexible, but what about space?
Well, even before Einstein, Galileo had some crucial insights into the nature of motion. He realized that there's no such thing as absolute rest. All motion is relative to the observer's frame of reference.
Oh, right. You had that great example with the train in your notes. If you drop a ball on a stationary platform, it falls straight down. Same thing happens if you drop it inside a train moving at a constant speed.
But if the train suddenly accelerates or decelerates, the ball appears to curve, even though no force is acting on it horizontally. It's just that the train is no longer an inertial frame of reference.
So how we perceive motion depends entirely on our own motion.
Exactly. And this principle of relativity held true for centuries. But then, in the mid-1800s, James Clerk Maxwell came along and unified electricity and magnetism. His equations showed that light itself is an electromagnetic wave traveling at a constant speed.
But that created a problem, didn't it? If light travels at a constant speed, what is that speed relative to? It seemed to imply there was some absolute underlying medium called the ether that light propagated through.
Right, but this ether idea, it created a conflict with Galileo's relativity. Why would the laws of electromagnetism be tied to this absolute frame of reference when everything else seemed to be relative? It just didn't fit.
And this is where Einstein enters the picture again in 1905 with his special theory of relativity. He basically said, let's get rid of the ether altogether. Maxwell's equations are right, the speed of light is constant, and that's it. No need for an absolute frame of reference.
But that seemingly simple statement had some pretty radical implications. If the speed of light is constant for all observers, regardless of their motion, then space and time themselves must be flexible. They have to be able to stretch and shrink depending on an observer's relative velocity.
It sounds crazy, but there's actual experimental evidence for this, right? Like that famous muon experiment.
Exactly. Muons are these subatomic particles created high in the atmosphere. They have a very short lifespan. According to classical physics, they shouldn't even be able to reach the Earth's surface before they decay.
But we do detect muons at ground level. So how is that possible?
Because of time dilation. From our perspective, time slows down for those fast-moving muons, giving them more time to reach the surface before they decay. And from the muon's perspective, the distance to the Earth's surface actually contracts due to its high speed.
So it's like time and space are working together to make sure the speed of light stays constant.
Precisely. And then there's the concept of the relativity of simultaneity, the idea that there's no single universally agreed upon now.
Right. It's like that thought experiment with the train. If you're standing in the middle of a train carriage moving at a constant speed and you shine a light pulse, you'll see the light reach the front and back wall simultaneously. But for someone standing on the platform, those events won't be simultaneous.
Because the back wall is moving toward the light pulse and the front wall is moving away. So whether two events happen at the same time depends entirely on your frame of reference. There's no absolute now.
Okay, so Newton's view of absolute time and space has been replaced by Einstein's relative space-time. But what about gravity? Newton had his law of universal gravitation, but how did that fit into Einstein's new picture of the universe?
That was the big challenge. Newton's law of gravity depended on the concept of instantaneous action at a distance. But Einstein had shown that there's no such thing as simultaneity in the universe. So he needed a new way to understand gravity that would be compatible with his theory of relativity.
And that led him to his general theory of relativity, the idea that gravity isn't actually a force, but a curvature in the fabric of space-time itself, caused by the presence of mass and energy.
Exactly. So instead of thinking of the Earth pulling on an apple, Einstein's theory says that the Earth warps space-time around it, and this warping creates what we perceive as gravity. It's like placing a bowling ball on a trampoline. The ball creates a dip, and that's what causes objects to fall towards it.
And this theory has been incredibly successful, explaining everything from the orbit of Mercury to the bending of starlight around massive objects. It even plays a crucial role in how GPS systems work.
Right. So the takeaway here is that gravity isn't a force in space-time. It's a manifestation of space-time itself.
So, to recap, we've got no universal now. Time and space are flexible and can be warped by motion and gravity, and simultaneity is relative. It's a pretty radical departure from our everyday experience of reality. But then, as if things weren't strange enough, along came the quantum revolution, revealing a whole other layer of surprising truths about the nature of, this time at the tiniest level, the world of atoms and the particles within them.
Absolutely. The age-old philosophical question of whether matter is infinitely divisible eventually led to the concept of the atom, the supposedly uncuttable building block of matter. But for centuries, it remained largely a philosophical idea. There wasn't any real scientific evidence to support it.
Right. So how did we go from this philosophical idea of the atom to actually proving that they exist?
Well, it's interesting. One of the earliest clues came not from a physicist, but from a botanist named Robert Brown. In 1827, he observed pollen grains jiggling randomly in water under a microscope. This became known as Brownian motion.
And at the time, no one really knew what was causing this strange.
Right. It wasn't until 1905, the same year he published his work on special relativity, that Einstein provided the explanation. He realized those pollen grains weren't moving on their own. They were being constantly bombarded by countless water molecules, far too small to be seen directly.
So even seemingly still water is actually teeming with motion at the atomic level. It's like if you could zoom in and see those water molecules, it would be like a mosh pit down there.
It's a good analogy. And Einstein's work didn't just explain Brownian motion, it also provided strong mathematical evidence for the existence of atoms and just how many of them there are. It finally moved the atomic theory from the realm of philosophy into the realm of scientific fact.
Wow, so it started with a botanist looking at pollen. That's pretty cool. But then, just as we were getting comfortable with the idea of atoms being the fundamental building blocks of matter, it turned out they weren't so fundamental after all, right? Scientists discovered that atoms themselves were made up of even smaller particles.
It's exactly. The late 19th and early 20th centuries were a period of incredible discovery in physics. Henri Becquerel and Marie Curie discovered radioactivity, showing that atoms could spontaneously decay. Then J.J. Thomson discovered the electron, a negatively charged particle much smaller than an atom.
And then there's Ernest Rutherford, often called the father of nuclear physics. His famous gold foil experiment in the early 1900s was truly revolutionary.
Absolutely. He fired alpha particles, these tiny positively charged particles, at a thin sheet of gold foil. And to his surprise, most of the alpha particles passed straight through the foil, but some bounced back at sharp angles.
And that led him to the incredible realization that most of the atom is actually empty space.
Exactly. The vast majority of an atom's mass is concentrated in a tiny, dense nucleus at the center. The seemingly solid atom is, well, almost entirely empty.
It's mind-boggling, really. The objects we see and touch every day, they're mostly empty space at the atomic level. It's like an illusion of solidity.
Precisely. And then Henry Moseley used X-rays to determine the number of protons in an atom's nucleus, its atomic number. This led to the modern arrangement of the periodic table.
So we had this picture of the atom emerging, a nucleus made of protons, and later neutrons were discovered orbited by electrons. But this model, based on classical physics, had a fatal flaw, didn't it?
Yes, according to classical physics, those orbiting electrons should be constantly radiating energy, losing energy, and spiraling into the nucleus. But atoms are stable. Clearly, something was wrong with this picture.
And this is where quantum mechanics comes in. It all started with Max Planck, who, in order to explain the spectrum of light emitted by hot objects, proposed this radical idea that energy, like light, isn't continuous but comes in discrete packets, or quanta.
It was a revolutionary concept, a complete break from classical physics, and Einstein, as he often did, took Planck's idea and ran with it. He used the concept of quanta to explain the photoelectric effect, which is the emission of electrons from a metal when light shines on it.
So light wasn't just a wave, it was also a stream of these energy packets called photons.
Precisely. And then Niels Bohr applied this idea of quantization to the atom. He proposed that electrons could only exist in specific quantized orbits around the nucleus.
Meaning those electrons couldn't just be anywhere, they had to be in these specific energy levels.
Right. And they could only jump between these levels by absorbing or emitting a specific quantum of energy. This model, while it had its limitations, explained the stability of the atom and why atoms emit light at specific frequencies. It was a huge step forward.
But what was it about those specific orbits that made them special? What determined those allowed energy levels? That's where Louis de Broglie came in with his truly radical idea, wave-particle duality.
He proposed that if light, which we thought of as a wave, could also behave like a particle, then maybe matter, like electrons, could also behave like waves.
So electrons weren't just these tiny particles orbiting the nucleus, they were also waves.
Exactly. And Erwin Schrödinger developed a mathematical equation to describe these matter waves. In his picture, the electron wasn't a point particle orbiting the nucleus. It was a wave spread out around the nucleus.
And the shape of that wave determined the allowed energy levels.
Precisely. So by the 1930s, we had this pretty good understanding of the atom, with protons, neutrons, and electrons, all governed by quantum mechanics. But then, as we mentioned before, the particle zoo started to expand.
Right. We realized that protons, neutrons, and electrons weren't the only fundamental particles. There were all sorts of other particles being discovered.
Like the positron, the antimatter counterpart of the electron, predicted by Paul Dirac, and the muon, a particle very similar to the electron, but much heavier.
And no one really knew why the muon existed. It seemed like an unnecessary particle.
It did, and the discoveries kept coming. We found that protons and neutrons weren't fundamental either, but were made up of even smaller particles called quarks. And now we have the standard model of particle physics, which describes all these fundamental particles and the forces that govern them.
And what's even weirder is that these fundamental particles, they appear to be point-like. They don't have any size at all.
It's true. So that solid apple you're holding, which we now know is mostly empty space, is ultimately made up of these point-like particles that also behave like waves.
It's enough to make your head spin.
It is.
Oh.
And this brings us to one of the most fundamental and mind-boggling aspects of quantum mechanics. Its probabilistic nature.
Right. Instead of existing in definite locations with definite properties, quantum objects are described by probability. It's like that analogy with the eggs in the fridge. There's a tiny, tiny chance that they could spontaneously tunnel through the wall of the fridge and end up in a different compartment.
It sounds crazy, but at the quantum level, that kind of behavior is possible. And it's all because of how we interpret the wave function.
Right. Max Born proposed that the wave function doesn't describe a physical wave, but rather a wave of probability. The amplitude of the wave at a particular point tells you the probability of finding the particle there if you were to measure its position.
And the act of measuring, of observing, seems to cause this wave function to collapse, forcing the particle to choose a definite state.
So it's like reality is fuzzy and undefined until we look at it.
And the double slit experiment really brings this home. When we don't try to measure which slit an electron goes through, it acts like a wave, creating an interference pattern. But the moment we try to measure which slit it goes through, the interference pattern vanishes and it behaves like a particle.
It's like the electron knows we're watching and changes its behavior accordingly.
And it's not just electrons. This weird, probabilistic behavior seems to be fundamental to reality at the quantum level.
But Einstein famously had a problem with this, right? God does not play dice, was his famous quote. He believed there must be some underlying deterministic reality that we just haven't figured out yet.
Absolutely. He spent a lot of time trying to find loopholes in quantum mechanics, looking for some hidden variables that would explain this seemingly random behavior. This led to the famous EPR paradox, a thought experiment designed to highlight what he saw as a fundamental flaw in quantum mechanics.
Right. The EPR paradox involved two particles that are linked together in a special way, such that their properties are correlated. If you measure the property of one particle, you instantly know the property of the other particle, even if they're separated by a huge distance.
And Einstein's argument was that this seemingly instantaneous communication between particles, it violated the principle of locality, which says that an object can only be directly influenced by its immediate surrounding. He thought there must be some hidden variables, some unknown properties of the particles that were determining their behavior.
So the question was, is reality non-local? Are particles somehow connected across vast distances?
And it turns out they are. Experiments based on Bell's inequalities, a set of mathematical relations that test for the existence of local hidden variables, have consistently shown that local hidden variable theories are wrong. The 2022 Nobel Prize in Physics was awarded for work in this area, confirming the reality of quantum entanglement and non-locality.
So Einstein was wrong. Spooky action at a distance is real.
It seems so. And this non-locality, this interconnectedness of particles across space. It remains one of the most profound and mysterious aspects of quantum mechanics. It challenges our very notion of what it means for objects to be separate and independent.
This exploration of both relativity and quantum mechanics naturally leads to the big question. Is there a unified theory that can reconcile these two seemingly incompatible of reality? Einstein spent the last part of his life searching for it.
He did, and it's a quest that continues to this day. The challenge is that general relativity and quantum mechanics, they speak different language. They describe reality in fundamentally different ways.
So on the one hand, we have general relativity describing gravity as the curvature of space-time. And on the other hand, we have quantum field theory describing the other forces of nature as interactions between particles mediated by.
And the standard model of particle physics, quantum field theory, has been incredibly successful in explaining the electromagnetic weak and strong force. It's one of the most successful theories in all of science.
But it doesn't include gravity, and attempts to incorporate gravity into the standard model or to quantize gravity have so far been unsuccessful.
Right. So physicists have been exploring all sorts of intriguing ideas to try to bridge this gap. Things like extra dimensions, string theory, M theory, loop quantum gravity, all sorts of mind-bending possibilities.
And symmetry plays a key role in all of this, doesn't it? The idea that the laws of physics should be the same regardless of your position, orientation, or motion in the universe.
Absolutely. And this principle of symmetry, it leads to some of the most fundamental conservation laws in physics, like the conservation of energy, momentum, and angular momentum.
And the standard model itself is based on these deep symmetries, known as gauge. These symmetries are related to the forces between particles and give rise to conserved quantities like electric charge.
Exactly. And then there's supersymmetry, which proposes that every known particle has a supersymmetric partner particle. It's a beautiful idea, but we haven't found any experimental evidence for these supersymmetric particles yet.
And then there's the ADAS-CFT course, which is a mind-boggling mathematical link between a theory of gravity and a particular kind of space-time and a quantum field theory living on its boundary. It suggests that gravity might emerge from a lower dimensional quantum system, kind of like a hologram.
It's a really profound idea that hints at a deeper connection between gravity and quantum mechanics, and it might even help to explain the black hole information paradox, which is the question of what happens to the information that falls into a black hole.
It's incredible how far we've come in our understanding of the universe, but there's still so much we don't know, like the mystery of why there's so much more matter than antimatter in the universe.
Right. That asymmetry is crucial for our existence, but we still don't fully understand why it happened. And then there's the transactional interpretation of quantum mechanics, which suggests that interactions between particles involve a kind of handshake that travels both forward and backward in time. It's a very different way of thinking about cause and effect.
And it all raises these deeper philosophical questions about the nature of science itself. Are we just creating increasingly sophisticated mathematical models that approximate reality? Or is there some ultimate truth out there that we're striving to discover?
And if reality is this strange and elusive, it really makes you wonder, what are we? Are we just collections of atoms governed by the laws of physics? Or is there something more to consciousness, to the experience of being alive?
It's a question that's been pondered for centuries, hasn't it? Like that ancient ship of Theseus paradox, where you replace every plank of a ship over time. Is it still the same ship? And if our bodies are constantly replacing their atoms, are we still the same person?
And then there's the even bigger question of how consciousness arises from matter. We've made incredible progress in understanding the brain, but the subjective experience of consciousness, it still feels like a mystery.
Some have proposed that consciousness is an emergent property of complex systems, like how the complex organization of an ant colony emerges from the simple behaviors of individual ants. Maybe consciousness emerges in a similar way from the complex interactions of neurons in the brain.
It's a possibility. And then there's panpsychism, the idea that consciousness is fundamental and might be present in some form, even in simple particles. It's a radical idea, but it's interesting to consider.
But let's shift gears a bit now and talk about the perspective presented in the philosophical essence video. This video takes a very different approach, emphasizing the role of our perception in shaping reality and even suggesting that the past might not be as fixed as we think.
Right. And the video starts with a quote from physicist John Wheeler. No phenomenon is a phenomenon until it is an observed phenomenon. In other words, reality isn't real until it's observed. Pretty radical statement.
It is. And Wheeler's famous delayed choice experiment takes this idea even further. It suggests that the way we choose to observe a photon in the present can actually influence whether it behaved as a wave or a particle in the past.
It's as if our observation in the present can somehow affect what happened in the past.
Exactly. And the video goes on to apply this idea to our personal lives. It suggests that our past limitations and failures, they might not be as set in stone as we tend to believe.
It proposes that we can actively participate in rewriting the script of our lives by consciously shifting how we observe both our past experiences and our future expectations.
And they even offer some practical techniques for doing this, like the quantum journal method, where you write down your desired future outcomes as if they've already happened.
Right, it's a way of priming your brain, getting it focused on those possibilities. And then there's the observer's filter technique, where you choose something specific to focus on and you suddenly start noticing it everywhere.
It's like how when you buy a new car, you suddenly see that same car everywhere. It's just your brain becoming more attuned to what you're paying attention to.
Precisely. And then there's the time rewriting meditation, where you visualize past painful memories unfolding in a more positive way. The idea is that since our brains don't perfectly distinguish between memory and imagination, repeatedly experiencing the past in a new light can actually rewire neural pathways and change the emotional charge associated with those memories.
So it's like consciously choosing to see the past in a different way, which can then affect how we feel about it in the present.
Exactly. And the video brings up the double slit experiment again, highlighting how quantum particles exist in this fuzzy, probabilistic state until they're observed. It's almost as if reality is waiting for a conscious observer to define it.
And they also talk about the placebo effect, which is a well-documented phenomenon where our beliefs and expectations can have a real impact on our physical health.
Right. And this all points to the idea that our minds play a much more active role in shaping our reality than we typically give them credit for. Our expectations, both positive and negative, can have a huge impact on our lives.
The video suggests that our lives operate as a kind of self-correcting loop that tends to mirror our dominant expectations. So if we're constantly expecting negative outcomes, that's what we're more likely to experience.
But the good news is that we can hack this loop. We can consciously choose to observe a different reality, and that can start to shift things in our favor.
And they lay out a 3-step observer's method. Define what you want to observe, act as if it's already happening, and then look for evidence to support that new observation.
It's about becoming a more conscious and intentional participant in creating your reality.
And they even suggest that the past itself is open to reinterpret. Wheeler's idea that the past only exists as a result of our observations is revisited, suggesting that even our past experiences are still in flux to some degree.
It's a fascinating idea that challenges our usual linear view of time, and it ties in nicely with the concept of time loops and alternate realities.
Right. The video talks about how we've all had those moments where a seemingly small decision leads to unexpected consequences that ripple back and affect our past in a way. It's like that example of taking a different route to work and ending up meeting someone who opens up a whole new opportunity.
It makes you wonder if there's a deeper connection between our present choices and the seemingly fixed events of our past.
And the video talks about the importance of mindful living, of being fully present in each moment and recognizing how our choices, even small ones, can have far-reaching consequences.
It encourages us to become more aware of the loops and patterns in our life, those recurring behaviors and thought patterns that shape our reality.
And by making small, intentional changes, what they call conscious iteration, we can gradually break free from negative patterns and create more positive.
It's about cultivating a mindset of experimentation, of playfulness even, in approaching our lives.
And the video suggests that even those moments of déjà vu, or those recurring patterns that feel like we're stuck in a time loop, they can be opportunities for growth. By making a different choice, by approaching the situation with a new perspective, we can break free from the loop and create a new reality.
And the concept of alternate realities, it's presented not just as a scientific theory, but as a framework for thinking about the possibilities that our choices create. Every decision we make, it potentially leads to a different outcome, a different reality.
So it's not about trying to control every aspect of our lives, but about recognizing that we have agency, that we can choose the path to take.
And the video emphasizes that these alternate realities, they don't have to be drastically different. Often it's the small, incremental changes that make the biggest difference in our happiness and well-being.
And they even suggest that our regrets can be seen as valuable lessons. Those paths not taken, they offer us insight into our values and desires, helping us make more informed choices in the present.
It's a really empowering perspective that encourages us to take ownership of our lives and to recognize the power we have to shape our own reality.
It's fascinating how these ideas about the power of observation to shape reality, they echo some of the most mind-bending concepts in physics, like the double slit experiment and quantum entanglement.
It does make you wonder if there's a deeper connection between the quantum world and our own conscious experience.
And then there's the even more speculative realm of time loops and alternate realities in theoretical physics.
Right. Things like closed time-like curves, which are theoretical pathways through space-time that could potentially allow time travel. And the many worlds interpretation, which suggests that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome.
It's mind-blowing stuff. But even if those theories turn out to be wrong, the idea that reality is more fluid and less fixed than we typically assume, that's a powerful concept.
It is. And it brings us back to the practical techniques that the Philosophical Essence video offered for shaping our reality, like the time rewriting meditation, where we consciously choose to re-experience past memories in a new light.
And the three-step observers method, where we define our desired reality, act as if it's already happening, and then look for evidence to support that new reality.
It's about becoming more aware of the self-correcting loop that our lives operate in, and then taking conscious steps to change that loop, to create a reality that's more aligned with our values and desires.
Well, this has been an incredible journey, from the tiniest particles to the vastness of the universe, and then back to the very personal realm of our own minds and experience. It's really made me rethink what reality even means.
It has for me, too. It's clear that reality is much more complex and multifaceted than we often assume. And the more we learn about the universe from the smallest particles,